Okay, so ready to go. Thanks again for joining us for this workshop. You can see all the participants, by the way. You can enter also comments. If you want to ask questions, you can enter them on the chat and we'll take them as we move along. But here is the agenda for the first session. We have an introduction. We've already spent a bit of time with the introduction, so we're going to not follow exactly the time here, but roughly this is the schedule. So there is an overview with the industry case studies, and then we have 3 presentations, short presentations on the seasonal climate forecast to do with downscaling and bias correction, skill, probabilistic forecast and bias correction again, and multi-models. And then we have about 15 minutes, I think it's going to remain about 15 minutes for the discussion on multi-model combination. So, and then just to wrap up. In the afternoon, we'll have another session after an hour of break between the first and the second, and that's more around economic evaluation and the trial climate services. So let's start with this overview. The SECLI-FIRM project, for those of you who don't know it, is a research and an innovation project under H2020 European funding. So that's the structure. So there's a component of research and a component of innovation. And in terms of research, we do we focus on enhancing the forecast skill and multimodal combinations for then use in the innovation part, which is the application of the forecast, seasonal forecast to case studies led by industry partners or immediate stakeholders. And then also we produce trial climate services for industry case studies. And we have quite a lot of interaction amongst all these components, as you can see here from this PERT chart. We've got 9 case studies, which are actually more like 11 because some of them are split, and we'll hear about them later. But it's the main thing to understand here, without going into the details, is that we have a nice variety of cases with different geography, different industry sectors, and so on. So we'll hear about that soon. So that's the building blocks of the project, and one of the main goals is to assess the value of using the seasonal forecast. Most of the time is compared to the current status, which is using the climatology information. So this is a kind of simple schematic that we use to start with. Of course, things are more complicated than that, but it's a useful diagram to refer to, so we know roughly what we want to achieve. And that's basically a differential between what is being done at the moment with the climatology and what we are doing with the project using seasonal forecast. So we've assessed in the project various economic assessment methods to understand which is the best method to apply to each individual case study. So we spent quite a bit of time analyzing and assessing each individual case study, and looked at the various methodologies to assess the economic value. And this is going to be discussed in the second session in more detail by Nicholas. And we've in the process we've actually introduced very useful tool, which is the decision trees, and this has helped the connection between the industry partners and the decision making and what is actually required from the science in order to achieve that economic evaluation. So these are just tools that are aiding the discussion, very useful. And so each case study has its own decision tree, and we think it's a very good innovation also of the project. In terms of the research component, we've first of all set up a data set, like a very rich data set or database, which contains a lot of models, systems, seasonal forecast systems. So we've got more than 10 both from C3S, so European based, but also from America and from Japan in one case. so the Japanese model, in fact, and we have them on one platform, which helps with the interaction amongst the projects. So we pre-selected some variables. Of course, we haven't downloaded the whole archive of C3S, otherwise it's meaningless. But having them on the same platform helps also with the speed of access to the data. So that's very useful. And we've then looked at, we're going to look some of these results in the next session. So I'm going to go quickly through this. It's the various aspects of the research. So one is exploiting teleconnections to improve forecast skill. Another one is to look at weather regimes or indeed variations to it. So looking at how the distribution shifts compared to the seasonal mean. And in another case, we look at statistical downscaling and with also a bias adjustment. So there is a combination of the two here. We're assessing different methodologies also for downscaling. And we'll hear about that also after my presentation. So I'll go quickly here to the next one, and the next research component is around looking at extremes to help frame the forecast in the context of the past situation, so we know how frequent or not are extremes. And then we go to the case studies. So before we get to the case studies, we prepared a video. We got actually two videos, one for case study 7 and one for case study 1. I'm going to show one of them. These are videos that were produced to assist with the communication of what we do in our project, and they were also suggested by our advisory board, and so we try to make them as simple as possible to make them understandable by, especially the goal was to get to managers of industry partners so they can communicate internally the benefit of using the results of the project. So let's hear this video for 2 minutes, and then we go to each case study where the case study leads will present. So please also get ready, the case study leads.
Luke and his team work for an energy company and need to forecast power prices a few months in advance in order to improve risk management and mitigate the impact of extreme climatic events. He knows that climate factors, such as heat waves, contribute significantly to power demand spikes and the resulting price increases. But he needs to properly forecast and identify the best strategy to anticipate these future market scenarios. One day, Luke attends an industry webinar where he hears about SECLI-FIRM and the research other companies are doing to improve energy risk management. He discovers that using seasonal forecasts and meteorological variables can help his company predict future market scenarios a few months ahead to adjust their market strategy. Luke and his team are now learning how to use the data produced by SECLI-FIRM to improve his company's forecast process and effectively manage the market risks associated with extreme climatic events.
Okay, so that was the short video, and hopefully it was self-explanatory to, oh, sorry, I meant to go to this one now. Okay, so now we have the 9, which are actually 11 case studies. You will see why there are 11, but I'm going to ask the case study leads to present them, please. So case study 1 is going to be presented by Gaia at ENEA, I believe. If you can unmute yourself, Gaia, and
yes, hi. So Marco was supposed to be here, but he couldn't. So for case study 1, we decided to tackle the problem of a heat wave during July 2015 that that was over Southern Europe. And particularly for Enel, it was a problem because we got higher temperature than normals, which were not properly forecasted, and therefore the power price raised with respect to what forecasted, and therefore we got serious problems about it. So we couldn't properly forecast the market scenario. So what we did was to try to use the System 5 forecast, or the ECMWF forecast, in order to try to see whether we could improve what the previous forecast that we got with normal values that were normally used at Enel before SECLI-FIRM. So at the moment, we use a method that was this is called the weighted mean, which is actually not really used. So we improved actually what we could see in July 2015, but we see that we didn't reach this extreme target. So this is the central panel. So what we could say is that ERA 5, which we use as and the observed value in July 2015, is not properly caught by this this signal, and this is reflected also to the power demand model in the right panel. So you could see that forecasts from 5, 3, and 1 month in advance before July 2015 are not really different. And we with this method, so with this weighted mean, at the moment we couldn't reach reasonable results, but we are of course working on different methods together with the SECLI-FIRM work package 2, so the scientific community, to improve this result. So we are going to test other methods.
Okay, thank you, Gaia. And I believe you're going to present also this one.
Yes, sorry, I wasn't muted. So yes, so for case study 2.
So this is 2A,
yes.
yes, this is 2A, and then we have 2B. Yeah, thanks.
Yes, this case study is shared with Alperia, so another stakeholder. So for on Enel's case study, on Enel's side, we case study 2 treats the drought that occurred in winter 2015-2016. And so it means that we got warm winter, so low power demand, and we got not much hydro energy, because it was a dry winter, so there was no rain, as you can see in the central panel. Especially the red bar are the observed values of rain, and you could see that, for example, in November 2015 we got a negative anomaly, a big negative anomaly of rain. And so again, in this case study, we use the weighted mean of System 5. So this old method, the first method that we tried with SECLI-FIRM, in order to see whether we could improve our results. And again, here we got some nice hints. So for a few months we got some values that were different from the normal value, so the one that we used before at Enel, but still we for example for November 2015 we are not satisfied with this results, because we couldn't see again the big negative anomaly that we got. And this but however, when we see the right panel, so when we translated this climatic information to our production anomalies on the Alps, we could see that still we are improving with respect to the old method that we were using at ENEA. But still, so as I said before, we are going to test other methods that are suggested by SECLI-FIRM in order to improve these results in the production on Alps and Apennines.
Okay, thank you, Gaia. And now we have case study 2B, which is the twin of 2A on still kind of same season and drought. And Valentina is going to present it, please.
Hello, Alberto, and good morning, everybody. Alperia is an energy utility in South Tyrol, in northern Italy. As an NLK study, also Alperia is taking into account the mild dry period between 2015 2016, to which apply the URAC forecast model, which considers not only temperature and precipitations, but also the volume of snow melt. The snow melt is really important for the hydropower production in Alpine region. Alperia is considering an only valley in the northern Italy with the 6 hydropower plants in series and the complex management. By now, the results that we obtain are comfortable.
Yes.
Thank you, Valentina. And okay, yeah, back to case Gaia, please. Thank you.
Yes, sorry. So for case study 3, we investigated on our wind production. So during March 2016, we got few days of high wind that brought to a higher wind production and lower market prices, while during for example for the 10th of March we got low wind that increased our market prices. So the idea would be to have forecasts in order to foresee this wind production and therefore market prices during these days. So at the moment we are testing monthly values of wind in order to understand whether what could be the regime, the monthly regime of wind in southern Italy. Because it's where we get the largest amount of power plants there, and so what we could see again by using System 5 monthly wind forecast and applying the weighted mean approach is that not in many cases we couldn't foresee the anomalies of wind that we wanted, but we are aware that at the moment we are using monthly values, and let's see what's coming up with the next approaches that SECLI-FIRM suggests. Also because we are foreseeing to use probably downscaling, so in order to for example improve the resolution of wind, the spatial resolution of this variable in southern Italy. So please next, I guess, yes. So again, so for case study 4, Anna studied, so we work in other countries like Spain and Colombia. You will see case study 5, and for case study 4 we investigated periods of high and low winds in Spain during winter 2014 and on winter 2014-15. And so what we could observe in this, so we picked, as you can see from the right maps, we picked 5 points where we have wind farms in Spain, and which were the most representative for the wind production in Spain. And we again tested what system 5 could see during the periods of interest, and again here we got the same results as Italy. So we got some improvements for some months, but still we should work more on with the scientific community of SECLI-FIRM in order to improve such results.
Okay, thank you, Gaia. And last one for you, I think.
Yeah. Yes. So for case study 5, so we focus on Colombia, and we focus on again on the winter during a strong El Nino, where we got high temperatures and high rainfall. And so here we started investigating a bit on the data we got. So not only on system 5 forecast, but also on ERA 5, which is our data set of, let's say, that represents our real weather at the moment, real climate at the moment. And what we could see is that we got some overestimation of rain with ERA 5. So during SECLI-FIRM, also of course with the advice of the scientific consortium, we decided to use another approach and replace a ERA 5 with some station data that we got in our basins of interest. And on the right panel, you could see, for example, an example for one basin where we translate the rain that we got from system 5 forecast with it on a station data set on the, for example, Gatape Basin, and we translate the rain forecast to the inflow, which is the variable that we are interested in for hydro production. And what we could see is that that forecasts are not so bad actually in Colombia, and we could reproduce nicely the inflow. Of course, we know that this forecasts are really close to the normal values of the stations, but still they give nice results. So, and in this case, we will try again this downscaling, for example, which could help in the for smaller basins like this Gatape Basin. Yes, I think I'm done.
Thank you, Gaia. And now we've got 5B, so the twin of 5, still in Colombia, but this time is led by UL, BWS. I believe Kristian is presenting it, please.
That is correct. Hi, everyone. My name is Kristian Nielsen, and as Alberto just said, I work for UL. And together with Celsia, who has represented the stakeholder for our part of this case study, we're also looking at the hydropower production in Colombia. And we have tried a couple of different ways of actually forecasting this. We have tried a more direct forecast, which is quite similar to what Gaia just represented from Enel, where we're also looking at a forecast for this specific area and taking a direct correlation between some of these variables and river flow, which is what you see in the top part here of the two different pathways. Besides that, one of the other things we've also worked on is to try to use teleconnections to actually get a more skillful forecast, because as Gaia also mentioned before, Colombia is one of the places where there is actually quite good skill in seasonal forecast, especially compared to Europe. So therefore, we've also tried to look a bit on using a teleconnection with the sea surface temperature anomaly patterns, actually in a global scale, to come up with something that might be more skillful. One of the issues, as Gaia has also mentioned, is that in Colombia, some of the areas we work at are so small that using the direct forecast becomes at least difficult because of the very special, not special, but the very unique topography of the Andes and the valleys in this area. So therefore, we are also working in using teleconnections as a more skillful forecast. I think that was it for me.
Okay, yeah, thank you, Kristian. And now we move into case study 6. And I believe Gertie is presenting. Or...
Yeah, Yes, that is correct.
Thank you.
Hi, my name is Gertie. I'm from KNMI, the Dutch Meteorological Institute. The stakeholder is TenneT. Martijn de Ruiter is also present, I think, in the audience. And it's about maintenance and operational purposes of for wind parks, and the preferred methods of access is by boat. Can you see my mouse? I guess not.
No, because I'm controlling the presentation. Yeah.
Yeah. Okay. So on the left top, you can see the hub for which TenneT is responsible, and a little boat. In this case, a little boat which is going to the wind park. The thresholds are given for wind speed and significant wave height, and these are dependent on the specific vessel which is used. And on the left bottom, you can see the wind park Borselen, the location with respect to the Netherlands. And on the top right, you see a recent example of a time series plot where I used the extended ensemble forecast and the first 11 members. On the y-axis, you see the significant wave height in centimeters. The blue bars, the top of the blue bars show or denote the thresholds. The blue line is the 10-minute observation line, and 10 minutes is very high resolution, and the red is the first member of the model forecast, and then added together so that you have one red line. In the gray, the first 10 members, and there are 51 members, the first 10 members are shown, given an idea of the spread in the ensemble forecast. And you can see that, well, I used here time series, it's for 19 March until start of May, so it's a recent example, just to show the possibilities of, in this case, this extended forecast. Of course, the practical visualizations are being developed and discussed with the end user TenneT, and we will use also the seasonal forecast and the short and the normal ensemble forecast. In this case, you can see that there is quite a good overlap between the forecasts and the observations, and the long periods of where the thresholds are being met is well forecasted. There's quite a large overlap with the next case study 7.
Thank you very much, Gertie, and good segue to case study 7 with Hannah from Met Office, and case study with Shell. So I believe Hannah is presenting this.
Yeah, good morning.
Hello, hi.
So case study 7 is being led by the Met Office with Shell as our industrial partner. The main aim of the case study is to illustrate the application of long-range forecast data to identify calm weather windows during seasonal shoulder months in the North Sea, facilitating earlier decision-making and reduce operational costs for the marine energy sector. So the approach that we're using is to use weather patterns to forecast significant wave height. The Met Office has a predefined set of 30 weather patterns, which are representative of the typical broad-scale atmospheric circulation patterns over the UK and surrounding area, which includes the continental shelf. And these broad-scale atmospheric circulation patterns typically have more predictability at longer lead times than specific weather or wave parameters themselves. By combining historical daily weather pattern classifications with historical wave conditions, we can build up a number of climatologies which represent the wave conditions that occur under each of the weather patterns at different times of year. And these can be combined with probabilistic weather pattern forecasts, with the result being a site-specific forecast of the probability of exceeding specified wave operational limits. With the presentation, which is shown in the central panel here, showing the deviation from climatology. And we'll be looking at both kind of these specific case study events that have been identified with Shell, as well as running some kind of longer term verification to assess the skill of this approach. And as Gertie mentioned, there's quite a lot of similarities between our two case studies. So we've been working with Gertie and the team at KNMI to run a comparison of the two approaches used in case study 6 and 7.
Thank you very much, Hannah. And now the next case study 8 is presented by Phil Bett at the Met Office also, and in collaboration with National Grid.
Yeah, hi everybody. Hope you can hear me. So case study 8 is our work with National Grid, focusing on the winter. The particular sort of events that initially triggered their interest were things like the Beast from the East event in very late winter 2017-18. Although there's been plenty other anomalously very cold and calm winters, which when it's very cold, obviously you have increased electricity demand, and calm, you don't have the wind power compensating for that. So these are the sort of key events that National Grid's interested in. We took, you can see from the slide here, there's sort of two different sort of approaches here, in that there's National Grid have this ongoing national demand forecast, and they also have this average cold spell ACS quantity that they calculate. And for both cases, we've got the challenge of going from something that we might be confident on with the seasonal forecast, something like a seasonal mean. That has to be translated into something a lot more usable by National Grid, usually with sort of sub-seasonal, sort of daily scale variability that we're interested in forecasting. So we've been doing a lot of work in figuring out how to go from that sort of seasonal scale forecasting down to the scales that are necessary. We've looked at using weather types, weather regimes in different ways. Things like the ENEA or other sources of seasonal forecasts. Looking at weather as well as forecasting the mean, we can forecast the variability within the season. We've also used this as a interesting way of applying our technique for looking at unprecedented climatological extremes, where we use the seasonal forecasting system, but not in a forecasting method, instead in a way just to sample the possible current day climatology in a way where we have more samples than the actual observations. And that's a good way of better evaluating present day risk, and that's particularly suited to this average cold spell method. I think that's all that I wanted to say on that. Like yes. I say, is weather types ties in with the other things as well.
So thank you, Phil. And the last case study is with, I believe, so this is also Met Office led with Thames Water. And is Kathy presenting this? Was Phil again? No. Do we have a presenter for this?
I think it was going to be Katie. If she's not here, I can say that it uses weather types and looks at water demand. The weather type methodology is quite similar to what's used in case study 7 that Hannah presented, actually, and has used a lot of the learning from developing that in producing something on the slightly more sub-seasonal timescale, useful for forecasting demand for the water industry in the UK.
Thank you. Thank you, all the presenters. As you saw, there is a very good interaction between science community and industry. That's the importance and the strength of the project, in fact, to have that connection to build this case studies. So there's a flow of communication between the science and the industry, which is quite innovative. And that's also in the spirit of the research and innovation project, as I mentioned at the beginning. And this case studies then will formally go into work package 4, and this is where the case studies are turned into trial climate services. And we've looked at various ways in which we can deliver the climate services. We run like a consultation with the industry partners, and we've come up with this table. We'll hear more about the Tri-Climate Services in the second session, so I won't spend too much time also because we are running a bit over time. So I'll go over quickly. I'll just give you a couple of examples of how to link, possibly link this decision tree with a visual demonstrator, or in this case, we have another way to represent the case study in a different visual way, but simpler. And so in the end, we'll have a number of options to demonstrate how the climate services can be developed. And that's, again, I think it's a strength of the project to have this portfolio of different methodologies. As I said, we'll hear more about this in the second session. And so with Joe Osborne from Met Office, so I'll leave it there for now. Just want to mention also that if you want to learn more about individual case studies, the case study flyers are available online, and they are regularly updated. There was an update a couple of months ago, and all of them are there with a 4-page flyer in most cases. In one case it's 5, but they follow the same structure. And so it should be easy to follow them. There is the rationale, the reason why we do the case study, and then the science and what solution is being adopted for each one. So that's there. We got videos also on website, so I encourage you to go. And also I forgot, sorry, Lucy, I forgot to mention the hashtag. Maybe it's not too late. We got still another part of the meeting left. So if you can note a hashtag and you want to tweet, I haven't monitored it, but hopefully somebody is tweeting about the workshop like we do when we are on a physical meeting. So here is the hashtag SECLI-FIRM without dash in between, and other ways to get in touch are also shown here. So with that, I'd like to stop, and we're going to take some questions. Thanks for people who have typed questions in. So maybe I'll need to go back to the presentation actually, because but hopefully we can achieve that without going back. One question, we're going to take 3 questions, and for the next 4 minutes. So questions, brief answers, please. Well, the questions are there, so I'm going to read them unless there's people want to ask quickly. The first one from Anka, if I can find it, the graphics that was asking about. Can you unmute and ask briefly the question, Anka, please?
Yes, sorry, Alberto, it's way too late. I was hoping that for the earlier case studies we got presented, we were told what's better, good, not satisfactory, what was blue, what was red. I didn't follow that, those graphics at all. It was just about clarification during the presentation. So thank you for coming back. But
yeah, maybe it's never too late. Yeah, we can. Okay, Guy.
It got better as we went along. So maybe somebody read that.
Okay, Gaia or Marco, would you be able to?
Yeah, sorry, Anka, I didn't read the question. So each color was representing one month of run. So
sorry, I don't remember the graphics, so this is really not relevant anymore.
You're,
the next time we look at any graphics. Thank you.
Okay, no problem.
Yeah, it was about this colors, blue and red. Sorry. Okay. I don't know, it's going very quickly now. I think you can see the... Yeah, I think it was about these colors.
Okay. So
if you can answer briefly, yes, please. Yeah, thanks.
Each color identifies, so the blue light and the blue identifies the month ahead. So sorry, there is no caption actually. So the dark blue is the 3 months ahead. So the forecast made the 3 months before of the case study. That was the end of 2015. The light blue identifies the 1 month ahead. So in this case is the forecast made on September 2015 for the quarter, October, November, December. And the red bar is the actual data from ERA 5 in this case. So it's the verification. So we can see, for example, in the, I don't know, case for November 15, the light blue is still wrong on the top, still wrong signal, but with minor amplitude. Or the December 15 for the case of ALTS, the light blue is just slightly better than the dark blue because it's the forecast that is close in terms of time to the event. So the ratio is the rationale is the dark bar is far from the case, and the light blue is closer to the case study in terms of time. I don't know if it's clear.
Yeah, I mean, this is also, you know, we're looking at precipitation in Italy, so it's quite a tough test, and on monthly averages as well. So it's a stress test, but yeah, we're doing pretty well. It's a bit better on the temperature, of course, but. Okay, thanks, Marco, and the question. So there are a couple of questions now, I think both for Phil, if you'd like to address them, please. So the first one from John Upton. Hi, John. Hi, teleconnections are proposed by some as important sources for seasonal forecasting, but others tend not to use them or actively do not use teleconnections. Is this due to global variation in connectivity of these systems, or is it also partly due to some institutions preferring not to use them?
I guess it just depends on the skill and exactly what you're looking for, I suppose. I think a nice thing that we've looked at in this project is that we have a section of work on teleconnections. We have another section of work on weather typing, another section of work on downscaling, and these are all different ways of going from things that we might be able to forecast on the larger scales down to something that we need to forecast for the users on other scales. And I think these are all techniques that, I mean, I'm not sure complementary is even the right word. They're all things that you'd want to look at and maybe use them all together or use them in different bits in different circumstances. And I think one of the nice things about being able to focus on case studies in this project is that you can pick the tools that are most appropriate or most skillful for the particular project you want. I think it would be wrong to approach this in a sort of dogmatic way, in that we always do it like this, we should carry on doing like this. I think exploring all the different possibilities is the best way to go.
That's useful, thanks, Phil. Yeah, I just wondered whether or not there was any sort of inbuilt preference within some organizations. It's just that it seems to work well in Colombia, and then that's fine, because teleconnections might be stronger and more linked to forecasting ability, skill in that region.
Yeah,
so that's useful. It's a general question, thanks.
Yeah, indeed. I mean, it depends on the strength of the signal of climate variation. So in Colombia, of course, there is ENSO, which is dominant and not so much, but this ENSO is not so strong in Europe, so we have to look at other things. So it depends on the season, the region, and so on, as well as what Phil has said. Okay, so and another question for Phil, could the principles of this work be applied? I think this is referring to case study 7 and 8 and 9. Could the principle be applied to other economic sectors based on their demand?
Yeah, I mean, I think all of this work is a really nice example of things you could do for other sectors. I mean, the nice thing about working with the energy sector is they're generally fairly receptive to working together, and there's a clear application. But yeah, anything like this, these methods can be, and the general idea of tailoring down from the large scale long-term signals down to something that's much shorter time scale specific for a user is something that could and should be applied to other sectors. Specifically about demand, I think it depends. So we started off thinking that the National Grid and the Thames Water case studies will be very, very similar because they're both related to demand in the UK, in winter specifically. in the end, we've diverged a bit more, and the approach we've used for Thames Water is now more similar to what we're using for Shell, the weather types on the more subseasonal timescales. Because we found that was a more practical approach in terms of getting something useful out. So again, I wouldn't sort of force one method on another case just because it sounds like it's similar. Just because one is demand and the other is demand, they must be similar. I think the general principles of exploring different ways of scaling down from something predictable down into something usable, I think those are the principles that would apply generally to other sectors as well.
Okay, thanks. And if your question is quick, Anka, would you like to?
So maybe if I just put it out there and see what other people in the conversation think about it. So firstly, I was wondering how much of the methodology is exported and exchanged between the case studies. We saw examples here, and we saw that some people found positive results, some people less positive results. Some people use a single model, as I heard from the Italian case studies. Is it necessary that other models might work or might not work? So I think the point I'm trying to make is, unless we understand why it was successful in a single case, extrapolating that conclusion beyond that case might be dangerous. We know that these are probability forecasts, so judging them on a single case is not very good at the best of times. And if I were an optimist, I'd say maybe if there isn't skill here where I'm really interested in the amplitude, maybe I need to modify my methodology. The pessimist might say, even if there was a success here, is it just a fluke, or is it really something that will add value every time such a circumstance would occur? So what I'm suggesting here is that maybe we need to think about, in the context of all the case studies, to think about why it is they were successful or unsuccessful, and maybe extend the analysis a bit further. It's just a thought I wanted to share with all the authors and the leaders of the case studies.
Yeah, okay. Yeah, thank you, Anka. And yeah, just to say that we are fully aware of the limitations, but we're also fully aware that it's always a question that comes up, you know, when you ask whether seasonal forecast works in specific cases, and that's why the project was set up this way. So the other thing to note is that we are still in the process of evaluating things. So these are preliminary results where you saw applying one system only. It's because we are going to apply the other systems as well. So it's going to be multi-model. And so just take them as a preliminary results, and building up on what you know, we can do, and extend. Also, we will have lessons learned and how we can extend as part of the final conclusions of the project when we get to that. And in fact, I didn't mention that we started about 2 years ago, over 2 years ago, and we have another more than a year to go. So that's now the hot phase of the project, when results are starting to come out, and then we'll analyze them, assess them, and look at lessons learned. I suggest that we are heavily over time. Not unexpectedly, but I would like to move on to the next session now with seasonal climate forecast. And if we have a 10-minute presentation each, please, and then some time, probably less than expected time for discussion on multimodal. But can we have, please, I don't know if it's Alice or Marcello or both who are presenting next. And then we have Phil Bett again, and Kristian again on multimodals, as you can see here. Marcello, Alice?
Hello, good morning. It's Marcello speaking. I will present for EURAC and ENEA the presentation on downscaling. So I can share my screen. No.
Yes. So Marcello from ENEA,
yep.
Petitta, and Alice Crespi from EURAC are presenting the next talk about downscaling calibration. Thank you.
Yeah. So I still have disabled the sharing screen, Alberto.
I'm going to give you. So I probably need to. So are you trying to share, yeah, and you cannot share?
Yeah, exactly.
Okay, so can you try now, please?
Yes, now it works. So just a second. I put it on. Okay, great.
Sorry, there was a little option here, hidden option, so I managed to get there.
Great. I hope you can see my screen.
Yes.
Okay, I try to. Great. Having also a red pointer. So I will speak about the downscaling, the bias correction for seasonal climate forecast. So the main problem here is also coming back to the question of Anka. It's try to create a general approach that could help all the partners and all the people involved in this project, but also beyond this project, to use a standardized approach for downscaling the data and using for all the case studies, all the different case study possible. So this is the general process, starting from the clear request from the users and try to have something that could go to higher scale and go beyond the normal resolution of seasonal forecast. Of course, what we try to do is try to do something at general scale, but I will show you that it's possible to using some other information for going more in detail for a specific aspect of an approach. So the main idea is to starting from the available data going to here at European level, and then using the data available going to a resolution of at least 0.25 degree. So the approach is based on using the SMWF seasonal forecast that has a spatial resolution of 1 degree. At least this is the one that is available on C3S, and using ERA5 as a comparative data set. This was done because since we want to establish a general approach, we want to give all the ingredients for all the possible users for replicating the approach. Of course, if you have other kind of data, you can improve both the bias correction and the downscaling. We try to show two different approaches, the downscaling and the regridding, with a bias correction, mainly based on quantile mapping. So what we will do is downscaling and regridding with a bilinear interpolation, and we compare the results using these two approaches, and then the bias correction based on approaches that are well documented in literature. So this is the first things that we will do. So we're starting from the temperature, mean temperature, and the monthly precipitation, and we computed the downscale part, and you can see for January and July, the downscaling approach based only on the regridding part with a bilinear approach, and then we apply a bias correction. You see in this plot and this other plot and all the plots that are more or less pinky and bluish, that the final bias after we apply the bias correction is relatively low for all the cases we are showing here. We also try to use another approach based on the linear combination of long-term means and monthly anomalies that have been combined to having 0.25 downscaled results. And then you see the different results before applying the bias correction, and you see that in principle the anomaly based downscaling, that is the one I show here with this formula, doing a better showing a better result compared to the bilinear downscaling. But after the bias correction is applied here in this 4 plot, the differences are relatively small, and we still can see some small advancement in the anomaly-based approach, but at the end are really comparable. So it seems that the quantile mapping and the bias correction play really an important role in this downscaling approach. So this is a general approach, could be applied everywhere because the data are for all the region of the world, are well documented, are based on existing literature. So what can be done more? I try to give you an overview of what was done by URAC in case study 2 that was already shown by Alperia. So the main idea is to try to use more data and try to see how the downscaling could be ameliorated in this approach. Let's see, this is a sketch of the valley we are studying and all the different lakes that are present and the streams. And so here is to try to combine data coming also from satellite and from in situ data with the forecast, with the seasonal forecast. So we see that we are going to use the soil moisture and the snow water equivalent that are present in the valley, combining with the meteorological data and try to forecast in the future and combining this data what could be the runoff. So of course this statistical model based mainly on machine learning approach. Of course, you can use different variables depending on what you are available, combining with the data that are in the seasonal forecast. But in general, you have to refit your model every time you are approaching a different system, a different period, and a different area. Doesn't work. Okay, this is a sketch, very general on how does it work. You see the super vector regression training is here and take data both from ERA5, snow water equivalent, from in situ runoff data and the data from ERA5. And of course, what is related to the prediction is based on the downscaled seasonal forecast and also other in situ data. In this case, I go directly to the conclusion for this specific case study. We can see that this kind of results produce better results than the climatology, of course, and this is very good, and especially for 1 month lead time. And what is needed is a long training data set that could be used for this kind of approach. With this one, I conclude my presentation, and I give you the floor to the other one and to Alberto for presenting or to question. I don't know what is the organization.
Yeah, thank you, Marcello. Yeah, we'll
stop to share.
Yeah, thank you. Yeah, we'll go through the presentations and then keep the questions for the discussion session after the 3 presentations. So it's over to Phil, please, now.
Hi. Let's see if I can share my PowerPoint. Right, hopefully you can see that now. Full screen it, great. Okay, so I had a fairly broad brief of the sort of things that I could be talking about today. So I've decided to sort of focus on some sort of key pictures, I guess, which hopefully illustrate some key points that I feel are important with thinking about seasonal forecasting and bias and skill and things like that. And hopefully I'll keep broadly to a good amount of time. So we obviously all have already mentioned that seasonal forecasts are probabilistic. They're produced as ensembles of forecasts. So I just wanted to illustrate sort of what the magnitude of the forecast spread is, the forecast uncertainty, because I think it's easy to forget that sort of thing. So we know forecasts are produced as ensembles, and we compare them against the observed climatology. So here we've just got observations on this plot at the moment. So these black crosses are 30 years, 30-year climatology, 1981 to 2010. Here it's UK average temperature. It's just a nice illustrative example. So this is the observed variability that we get. So we can divide it into quintiles in this case, divide it into different categories. So each of these categories, these different color blocks, gives a fifth of the years in that 30-year period. And you can produce some smooth representation of that historical climatology to give you an idea of which sort of temperature categories are more likely and that sort of thing. So that's what you really want to be comparing your forecast against. So obviously a forecast is an ensemble. So this is an example of a forecast. So these blue crosses in the middle here are a set of this is a forecast ensemble for a particular year. And I guess the key is that there's a lot of ensemble members and they're spreading over a very wide range. And you want to be comparing that against the observed range that's in black. And again, you can make a smoothed representation of that forecast ensemble as a probability density function. And there's lots of different ways you can do that. And I guess this is just an example, or you can use the ensemble members directly. And this sort of, to me, this really illustrates, this brings home why it's so important to use the whole ensemble or use the forecast probabilistically. So although there's this I think, very clear enhanced probability of it being a warmer than normal winter, you can see this in the clustering of the ensemble points or in the smooth distribution. It peaks up in these pink warmer ends of the distribution. And this blue distribution is higher than the white one underneath. It's enhanced probability. But you've still also got this colder than normal possibility here. It's less likely than an average year, but there's still a possibility that the year will be colder than average. And really we're spanning most of the observed range there. And well, it so happens for this forecast, the actual observation was up here in the warmest category. And we're broadly forecasting something like that. And I'd say we got particularly lucky in this case. But it just shows that difference between a single observation and the whole forecast ensemble and the whole historical observations as well. So you can use this in lots of different ways. The sort of traditional way that we talk about is we might use a threshold in the observations to define particular events of interest for decision making, yes, no sort of decisions. So for example, we might make a decision if the temperature is in this top quintile, this darkest pink section. So we might say if the temperature is in this warmest category, then we make some decision. And then you can use this, the probability distribution from the forecast to give you the probability of that event occurring. And this is the way we like to talk about using seasonal forecasts a lot. It's very logical from the point of view of the producers. But I'd like to sort of highlight something that we come up with against in this project quite a few times. How can we use this approach if we need to actually plug these temperatures through some downstream model that requires temperatures and not probabilities? And that's a problem that we've encountered several times in this project. You can think of some ways of getting around this. You can run your model multiple times, run your downstream model on all of the different temperatures from the ensemble. There might be other ways of approaching it. But that's a sort of difficulty that needs working around. And there's another one that I'm not entirely, I haven't got quite as an obvious answer for that. So what about when the usage is for some continuous function? Rather than making a yes/no decision, maybe our decision is more do this thing more or do it less. It's a continuous thing rather than a discrete thing. And that's where this sort of traditional approach of dichotomous yes/no events can break down a bit. And we have to think a lot harder about how we're going to use the forecast. And I think that's one of the places where the case study approach works really well. I just wanted to talk very perhaps briefly about skill. Skill is a property of the forecast system. It's not the property of a single forecast. It's not about the uncertainty of a single forecast like we were just looking at. It requires both hindcasts, running your forecast system over a historical period, and observations. And often our estimate of the skill is limited by either having not enough relevant observations over a long enough period, or maybe we can't run our hindcast model over a long enough period. So skill is an estimate, and it's an uncertain estimate at that. And often when we look at skill, it's often quite a noisy quantity, and there's lots of different ways of measuring skill. We don't need to go into that particularly here. Here's some examples of a simple measure of skill for 3 different forecast systems. I think all three of these systems are not being run at the moment. They're all a bit out of date, but it just sort of illustrates perhaps the sort of noisiness and relatively low levels of skill. Here we're looking at winter rainfall. I've drawn some yellow contours around what might be counted as statistically significant, so measurably different from zero, but really I think a lot of these little yellow contours you might be able to see are just noise. You get little yellow patches there that aren't really significant. So you have to approach things a little bit differently. Average over a large area is nice. So here's a nice example. I don't want to go into a huge amount of detail with this, but just an illustration of this is an approach that a colleague of mine's made recently. We found that if you average over a very large area here, sort of all of Northern Europe, then we can actually get significant skill in rainfall in the summer. And we never thought we'd be able to get seasonal forecast skill for rainfall in the summer. This was quite a surprise that we managed to achieve this, but it's achieved by averaging over a very large area here. So it's this green box, hopefully you can see in the map. This is a skill map. The color scale doesn't even go very high. This color scale is only to 0.6 in correlation. And you can see here a time series of the hindcasts and observations, and sometimes it's good, sometimes it's okay. Got some skill overall. And the year after that we published that skill, we happen to have again a very fortunate year in the forecast in that we managed to do very well with that. But that's just an example that illustrates that sometimes you might have to average over a very large area to get the skill. And that's where things like the downscaling that was talked about before really come in, because we might have the skill over a large area, but that isn't necessarily what's useful. So you have to make that connection somehow. This plot is really just illustrating what maybe a good forecast system looks like here in terms of a time series. So this happens to be not Europe, and there's a statistical model in this case as well as the climate model. But maybe just looking at the left-hand panel, this is a system that has some good skill measured in various different ways. The black line is observations. The green boxes are the 75% and 95% prediction intervals and a central estimate of the forecast. And I think what this shows really nicely is how wide the forecast probabilities are. Usually I think in every case, they're both sides of the line. They cover both above and below average in all cases. So this shows that the probabilities really are necessary to show which side is weighted more. We've also got, I think this is one case here where the observation lies outside the 95% prediction interval of the forecast. So just because the system has good skill doesn't mean it'll work well every year. Some years it's ridiculously close to the central estimate. And then sometimes, like I said, this case is even outside the 95% prediction interval. So I think this goes to what Anko had been saying before. Really, we need to assess the skill over a large number of years before then considering actually what that means for a particular case study year as well. So a system with good skill has got some good years and some bad years. Sometimes it gets the sign right in the central estimate. Sometimes the sign is wrong in the central estimate, but you hope that on average it'll do good. I just wanted to now just talk something about reliability. I'm not sure how much time I've got to talk about this, but this is quite an important additional thing that's separate to skill.
If you can do it in 1 minute, Phil. Sorry.
I'll do reliability diagrams in 1 minute for you. There we go. Okay, so the important thing about this is we're relating the forecast probabilities to observed frequencies. Can we rely on the probabilities from the probabilistic forecasts? So you need to define an event for this kind of assessment. So we say looking at whether the temperatures are above average. So let's just look at this example here, this particular dot. So here the forecast model said for this point we're saying this is all the times when this event, above average temperatures, were forecast with probabilities of 30 to 40%. But what actually happened, if we look at all of those times we forecast it with those probabilities, it actually only happened 10 to 20% of the time. So the forecast probabilities were not reliable. They didn't give us a good estimate of the observed frequencies of this event. I could look at another point, this point up here. This is where a point with all the times we forecast the event with probabilities of 50 to 60%, but actually out of those times, it actually occurred 60 to 70% of the time. So again, this isn't reliable in this case, where in this reliability diagram, all the points on our line are the line is too steep. It's too steep compared to the main diagonal. This is an example of an underconfident forecast. The low probabilities aren't low enough, the high probabilities aren't high enough. So this is a kind of thing where instead of a normal bias, a mean bias correction or a variance correction, we have to do something called a calibration, where you shift these points to the left or right so that they move onto the diagonal line. You can do this in various different ways. Of course, this sort of quantity is quite noisy in itself. Reliability, imagine it requires a lot of data to be able to break it down into all these categories. So here's an example from a reliable system. This is all fake data in this case. It's reliable by construction. So the probabilities can be relied on for decision making, but here the line still waves around a bit. So it's because of just sampling uncertainty, the limits of the amount of data we have, it still waves around a bit. You could calibrate it further. So that, I think, just covers all the sort of points that I wanted to make. Forecast uncertainty is often a similar sort of scale to climate variability. We're just looking at shifting that estimate a little bit by the forecast. The skill is uncertain, just like the forecasts are uncertain, and its skill is an estimated quantity. Just like we always expect to have to do some bias correction and variance correction to our forecasts, we should also think about whether our probabilities are reliable. We should expect to have to do some probabilistic calibration as well. And again, this point's come up a few times. In an ideal world, we just give forecasts of seasonal means averaged over large areas, but that isn't really what anyone tends to want. So this brings us back to the point of the project, where we're developing ways of using this forecast model output to things that are particularly useful for individual users as tailored forecasts. And this links to the downscaling, teleconnections, weather patterns, that sort of thing. That's all I've got to say on that. Only a few minutes over.
Yeah, thank you, Phil. Okay, so we're now moving to the third presentation, and then Kristian, if you can use your time for the presentation and move over to the discussion, just following your presentation, so seamlessly you guide us through the discussion. Yeah. Is that all right?
Yeah.
Okay, so you got, yeah, at this stage, we have basically 35 minutes, presentation and discussion all together.
Good.
Thank you.
Let me see, hopefully I can share my screen. So as always, if you cannot hear
me,
we're
going, for everybody, sorry, we're going to take questions after this presentation, so as part of the discussion session. Thank you.
Good. So what I would like to talk about is a little bit about the multi-model ensemble and the different combinations you can make. I think maybe I can move you away, Alberto. We'll go down here for a second. So I'll give you a brief introduction to this concept of multi-model ensembles. Then I'll show you some of the results of the specific methods we've used in SECLI-FIRM so far. And finally, we will move into the discussion about the potential advantages and limitations of using this weighted mean when you're combining models for the optimal combination. So first of all, what is the idea of using more than one skillful and also independent model, I should say here? If we look at the picture I've added here, you can see that, yeah, let's run through it fast, even though time is sliding a bit, that we have two model systems with 3 ensemble members each, represented by the black lines and the dashed lines. And for a specific time, which is just set as t here, they have a prediction of whatever variable it is that we're looking at. So if we start by looking at the A part of the figure here, you can see that each model is wrong, but they are wrong in each direction, which means that the final ensemble from combining two models will actually perform better than each of the individual models. In scenario B, however, we see that one model is performing better than the other model, which means that one model would actually perform better than the combined multimodal ensemble, but the combined multimodal ensemble will still be better than the other model. And since these models are both skillful, this will of course change in time. So, and of course beforehand, we don't know which model is the best model. So this will actually kind of equal out, you could say. And the same in scenario C that we have down here, where one model is performing better than the other model, which means compared to the combined multimodal ensemble, you would get one model performing better and the other one being worse than the multimodal ensemble. And again, same conclusion can be made. And therefore you would actually end up having skill by combining, at least if the models are skillful and independent, you will end up having more skill by combining the models into a multimodal ensemble. Alberto has already shortly mentioned here that we are looking at these 12 different models, some of them from C3S and others from the North American multimodal ensemble. And finally, as Alberto also mentioned, we do have a Japanese from the Japanese Meteorological Agency also included in our available models for SECLI-FIRM. So the question is now, can the skill be improved by obtaining the optimal combinations of models compared with just including all models in a simple multimodal ensemble that has all models? The way we looked at this so far is that we've looked at two variables. We've looked at temperature and precipitation at this point. This is because these variables from all systems lead us from, and also for energy, also for energy production. Handcast we're using was 1993 to 2016. Again, it covers all the case studies, and it's kind of the largest. It's the largest period we have available for all systems. The way we're kind of weighting the models is by looking at how well they perform, and this can, of course, as Phil just said, this can be looked at both probabilistically and also deterministic. The reason here, Phil just showed us that, of course, the optimal way is probably not to just take an average mean of all ensemble members. However, the solution that Phil gave in order to get around that some stakeholders actually want a number, and was in this case just to run all the ensemble members to the system. This, however, is not possible for everyone. So therefore, we still included a deterministic score, you can say, the correlation between anomalies here, just using the mean of all ensemble members, because there are some stakeholders that will need a final number and do not have the resources to run their decision systems as many times as there are ensemble members. Secondly, we are also looking at what model combination performs best probabilistically. In this case, we're looking at the Bria score at the moment. And so far, it's just for a binary event of colder, warmer, or drier, or wetter. The results I'm going to show you today is a monthly forecast with 1 month leads. So a forecast for February that comes out in January, or a forecast for March that comes out in February. Of course, this can also depend very much on the specific needs of the end user. So what I'm showing you now here is not all the possibility ways of using this. It's just to show you some of the results with some of the with at least one lead time here that is needed by some of the stakeholders in our case studies. And finally, yes, we are using ERA 5 as the reanalysis data to represent observations. So let me show you an output of how it looks when we actually try to find the best model combination. In this case, it's a monthly forecast with a lead of 1 month of 2 meter temperature anomalies. And this is over the domain of Spain. Actually, Portugal is also included here, I should mention. And this is for land only. So what do we actually see on this figure? Yeah, first of all, on the axis, we have the number of models in the combination. So you can see we have 1, 2, 3, 4, 5, all the way up to 12, where 12 includes all models and where 1, for example, is just a model by itself, not combined with any other models. And you can see here, this is a deterministic forecast. So this is just the correlation coefficient between the anomalies predicted and observed by the ERA 5. So yeah, as first mentioned, we can estimate we can easily here see that the single model for this specific region and this specific variable and this specific lead time, in this case is the ECMWF, which has a correlation of 0.286, so not really good correlation, but this is just to prove the concept to start with at least. We can also see that the best combination is actually not just to use all models included. All models included does improve slightly compared to the ECMWF. You can see the line here is, the gray line is slightly over the orange line. But there are actually better combinations, and it turns out that actually by only combining five of the 12 models for this specific case, you can get a better correlation. In this case, it would be a combination that includes both C2S models and also models from the NMME. This probably has to do with that these models are slightly more independent than just having models from the C2S, but also it has to do with the fact that these are models that perform well in average here. And finally, yeah, we've also plotted out a couple of the best combination only coming from European models, and finally also from all other models. Here's another different example. This time we're looking at Colombia. It's still a deterministic forecast here. It's just to show that even a direct forecast of temperature in Colombia with a lead of 1 month for land only here is quite skillful. You get quite a good correlation. The best combination here is including the NASA model, even though actually you could, yeah, it's hard to see here, but there are actually 3 models that performs better than the NASA model. But since the NASA model is probably more independent from the ECMWF model and the Meteo France model, it actually is part of the best combination here. Another thing we can show here, I think it's just another example. I think I'll run through this. This is for precipitation, again in Colombia. This is more specific for one of the case study needs, but let's, since time has slided a bit, run through this. So here's another example. Instead of using deterministic forecast of the mean of the sample members, we use a probabilistic forecast. So this time we're looking at this is temperature anomalies, and this is just 1 minus the Brier skill score. This is not, sorry, not Brier skill score, 1 minus the Brier score. It's not the skill score, that's what I wanted to point out. But the actual order of the models would probably be the same. This is only taking 10 sample members of each model at this case, just to not give anyone an advantage in having more sample members. The NASA model down here, however, only has 4 members, which is probably also why it's penalized a bit in this comparison I've done here. So we probably need to look at a different method, probably something called a fair Brier skill score or something similar. This was also for a different domain I can mention at this point, but it was just to show that this way of like actually testing all the combinations can also add skills even for a probabilistic forecast instead of a deterministic. So to sum up a bit, what you see doing this is, of course, that the best combination is often involving more than one model, which kind of leads back to the whole theory about why multi-models often outperform individual models, at least if they are somehow equally skillful and independent. Another thing is that the best combination often does not include all models here, which probably is another indication that some of the models are not skillful enough to actually be included. A third point is, as I've talked a little bit about before also, that in the observable mix, we often see that we have models that tend to be more independent models. And when I say independent models here, that's also something we've investigated into in this project to come up with an actual metrics that can find the independence between models. I'm sure Franco can inform you more if you have questions about that. And finally, we can see that all models are useful. That being said, that for a specific case in a specific area, it seems that all models at some place in the world for some specific variable are able to actually add skill to the best combination. So it varies very much depending on what you want to forecast, where you want to forecast it, and for what lead time, for that matter of sake, also you want to forecast things. Good. I think I will start out by taking, maybe we should start out by taking questions in general to the 3 presentations. So I think I will leave the word. Let me see if I can open the chat by having this at the same time. Let's see if there are any written questions we can start out with. I don't know, maybe we should start in order. Maybe some of the people that has written questions to the earlier presentations, if you would like to read them out loud, otherwise I can look for them.
I have a question from Shanti. I can see higher up. Shanti asked about how do we sell skill to a customer who's making a daily decision using weather forecasts, which again has got inbuilt error. I think, so obviously weather forecasts, they do have that uncertainty as well, but they're on much shorter timescales. The uncertainty is much smaller compared to a climate forecast, a climate prediction like a seasonal forecast. So I know that if I open my Met Office app on my phone, it doesn't give me an error bar for the temperature. It does give me a probability for rainfall. And I think most people are used to using that sort of information right now. So I think the comparison with weather is quite a useful way, a useful example where people are used to making decisions based on some probabilistic and some deterministic information. Obviously, the increase in skill it makes it quite a different sort of case compared to seasonal forecasting. So I think for me, I find it useful to think of seasonal forecasting as quite different to weather forecasting. It's not just weather forecasting with a longer lead time. But I think that difference in skill makes a big difference in how we expect to interpret it.
Thank you.
And there's something else that Anka mentioned about that perhaps I didn't really make the point very clearly, that I was talking about reliability and I talked about skill and how they're different things, and Anka's point in the comment is exactly right. You need both, that you can have something that's reliable with no skill, and you can have something that's skillful with no reliability. So it's I guess the point is it's important to check all of these things in as much as it's possible for the particular case you're looking at.
Philip, can I add one small comment to this? While reliability can be corrected by doing post-processing and doing the kind of analysis that's currently done in the case studies, other attributes of the forecast which matter, for example, the ability to distinguish between an event and a non-event, cannot. So they are intrinsic to the forecast system. They may or may not be represented in skill, they sometimes are. But this is, I think, the important thing to remember. Some things can be post-processed, others can't. That's why it's important to look possibly at other models if one model hasn't given you the answer that you need.
Yes, that's a very good point, thinking about what you can fix afterwards and what you have to fix beforehand. Yeah, very important.
Good. Did we have any questions on the... We can also hear if there are more questions for Phil.
Yeah, I mean, Kristian, can you read the questions there? There's one from Jan Dutton for you.
I can indeed. So we have a question that says, as the number of models included in the multi-model ensemble increase, the relative amount of data available for backtesting decreases. How did you avoid overfitting with a reforecast data set whose number of years is approximately the same size as the large MMME? As far as I understand the question here, for deterministic forecast, what we actually do is we just take the average of the models that are included. So we take, if we have two different models in a combination, we simply take the average of these two models, which means that we will have the exact amount of data points equal to the observational data from ERA 5 for each single combination, no matter how many models is represented. So per se, I don't think we have that issue. Maybe I'm understanding the question wrong. I don't know if Jan, you would like to extrapolate. Or anyone else in case.
Yeah, probably. Yeah, maybe Jan cannot speak. It's actually very early over in the US. Some surprising is up already, but since the start of it. Okay, so Jan said understood, so that's okay. Yeah.
Then we can move on to a comment by Anka, which is if error bars were added to this estimate of the scores, example was to allow for sampling variability, would the conclusion still hold? If not, the concept of best combination is not well defined. And I agree, Anka, we could probably have done something similar to what Phil has done here to include the error bars. This is for a 288 months that are combined together here. So hopefully the computation will still hold, but it's definitely still something that needs to be included. And I think we could do it by, for example, do something like Phil to even gather out the forecast compared to the observations. Yes. So yes, it definitely still needs to be included.
I think this is. I think this is what Andrea Alessandri just commented afterwards. There are methods to do this. I would be even more pragmatic than he's suggesting here. That is to say, I looked at the combination that you described as the C3S combination. That's no longer the case, and the systems that you used in that estimate are no longer the systems that give real-time forecasts now. So I would advocate the use of whatever models, set your sights on a particular set of sources and then look at them every time. As Philip showed, not even in models with relatively high skill, not each event is picked up correctly every time. Now, unless you know that a model is always going to give you the best answer no matter what, I think looking to see how much the models may agree or what the other models are saying is worth it if you can afford it. Because even if you were to put error bars and to come up with the best combination, by the time you do that, it may be that one of the systems in your favorite combinations has disappeared and no longer gives you a real-time forecast.
Can I ask which system is it that no longer gives real-time forecast by the C3S?
So, for example, Meteo France has changed forecast systems absolutely, definitely since you put that in. Okay. CMCC from next month will use a different system. The Met Office in 2 months' time will use a different system. So, so things evolve. I think having the tools in place to do this estimate every time you want to use the forecast and to decide which one to believe over others. But let me just give you the example of last winter. It was worth knowing that all forecast systems were in effect going for the same answer. I think that increases your confidence in that forecast more than the average skill evaluated however accurately over the hindcast period could have done.
For sure. Assuming yeah, I mean, as all models are skillful to some degree, it's of course give you higher confidence in the case. So for sure, it's also worth taking into consideration what the other models actually say in the specific case. Coming back to the changing in systems, of course, it's something that changes all the time. So you would have to, if you wanted the best current view on this, you would of course every time a system changes have to do this again in order to find the best combination. If you want to do it this way, yes.
If I can comment,
someone also.
Yeah. So yeah. I mean, what Kristian, just to add to what Kristian said. I mean, it's we have two different, two parallel things happening. One is the evaluation of the systems, just to give us an idea of where each system stands. And then we have the pragmatic approach that we need to take in order to select the models that we can and are available on a real-time basis, whether they change or not. And so the decisions we take on which model we use in the end may not be exactly the same as those that give the best answers. Noting also, of course, that the error bars might be such that all models could be just as well as good. But also in the, I mean, I don't know, I mean, I haven't tested it, but I don't expect more changes between two versions of the Meteor France model than, say, two Meteor France versus NCEP. So just as an example, I would expect a little continuity between one model or the other in the same, from the same institution. So of course they change, but they don't change dramatically, I don't think. But these are minor considerations given the practical approach that we need to take and then select the models, and we actually need to freeze them for a while. I guess we cannot keep testing things all the time.
Not within the project, at least. No, that would not be in a live setup.
Yes, yeah, that's right. Yes, yeah.
Also, I've written out here a couple of questions if people want to add or think about. We can read out one of them. For example, the bottom one says, is there a clear advantage in adopting an adaptive choice of models depending on variable region season as opposed to a global choice? And from what I've showed, of course, I would be tending to say that there is so big variances in the different areas and the different seasons that there would be a good idea in adapting a specific choice. There can of course be some physical limitations if you're a specific end user that needs several variables. For example, maybe it's hard to make a combined of these several variables of the best combinations of these and so on. So there are of course some limitations to this method of choosing the best model combination. Did we have more questions in the chat that I have missed? Yeah, the first question we've kind of already talked a little bit about it. Is there a strong argument for favoring a simple mean versus a weighted approach when combining multi-models? One of the things, yeah, we've already discussed it a bit. Maybe there could be more confidence in having more models included, especially in cases where they all show the same, as Anka said. And I don't know if anyone else has any further views on this. And yes, it's correct again, what you comment, Kristian, in the chat, that it is of course an issue that these models, they do change quite regularly. But again, as mentioned by Alberto, we need to be a little bit pragmatic in this study at least, and try to pick whatever we can see as the best solution right now. But in a live setup, for sure, there needs to be a strong focus, as mentioned also on the fact that these models do change quite often, and there are differences between model versions. We do also in our study actually have different model versions that we have tried to do this with, and you can see for some specific applications for some specific events, even model versions, they provide different results. But Alberto also mentioned we must assume, also I am not something, it's just my assumption here, we must assume that even between different model versions there will be some kind of continuity. They will be relatively similar in different skills regarding different events.
I can comment briefly here, Kristian. So one thing that is probably safer to assume is that the continuity in the model component would be strong. In particular, you are referring to the diversity, to the fact that the American models have significant differences and are more independent from the European models than the European models are amongst themselves. That will probably be a safe thing to assume. Whether the progression of skill would be slow or abrupt, we don't know. We hope it's a progression upwards. And this is something that I would just offer as an alternative to Kristian Viel's point of view that the frequent changes are a drawback. The alternative would be to know that you have a better system, a better model that you could put in your forecast system and sit on it simply because you think that users are so attached to having continuity and stability of their assessment of skill. I think that would be counterproductive. And it is a strategy that I know that, for example, the Met Office has adopted. The changes to the model configurations that go into the forecast system, if they lead to improvements in a forecast, you adopt them and you compromise elsewhere, maybe including in your stability of your information about how good that model is in relation to others.
Okay.
Yeah, I'd also like to comment on the fact that the changes in seasonal forecast models are actually less frequent than what happens in weather forecast. So seasonal forecast, we are relatively lucky. In weather forecast, they change every 6 months or so. So it's, and that's a given, whereas in seasonal forecast could be a year, could be 2, 3. So it's much more stable than weather forecast.
That is great. Good. I think we are also running into the last minute or two here. Correct me if I'm wrong, Alberto. So I don't know if anyone has any further questions or comments that they would like to share here at the very end. While you think, I would just like to thank you all for joining this session. It's been nice to see that so many people have taken the opportunity to join this this morning session, and hopefully a lot of you also stays longer. Not that we are done now, Alberto will take over in a second, but from my side, a thank you to all of you who's been part of it. So any last comments, questions?
So Kristian, are you satisfied with the
I think
answers?
we are also,
Yeah.
time-wise, I think we're getting close to it. So yes, so thank you again.
Okay.
And Alberto, I will leave it up to you again, and I will stop sharing.
Yeah, thank you. I mean, it's just really to wrap up and to lead to the next session. And also, maybe we can run a little exercise here. We've done it in another meeting, it worked well. So we'll try again here, see how it works. So the exercise is about taking a virtual group photo. So for those of you who are game, can turn on the camera now. You don't have to, but if you want to be in the picture, we're going to turn on the camera over the next 30 seconds or so. Then I'll take some screenshots, and then we'll also post them together with the presentations after the report, after the workshop. Okay, so let's see how many takers. I need to check also the photos. Wow, okay, good. Let me make it bigger. All right, so I may need to take more than one shot because we can only fit so many in the and actually, sorry, for some reason, I'm not able to, okay, 2. Okay, good. I'm going to give a first shot. If you want to smile for the camera, I'll tell you when. 3, 2, 1, now. Sorry, take another one, just for good measure. 3, 2, 1. Do you want to do, sorry, do you want to do a silly one? 3, 2, 1. Okay, and sorry, this is the first screen, and there are a few people over here, so I'm going to take another one. Not all of you will be in this one, but 3, 2, 1, go. And last one, just for good measure, 3, 2, 1, go. Excellent, thank you very much. You can turn off the camera if you want to. Let me check here. I get out of all this mess. Good. Excellent. So I am going to now just wrap up and just introduce briefly the next session, which will start in about an hour. And so I'm going to share the screen if I can see where sorry, I lost the control here. Where is it? Disappeared. Okay, maybe now. Share screen. Okay, so okay, so we discussed in this, just to wrap up, in this session we discussed we focused on the research side of the project. So it was more about the seasonal forecast, calibration, downscaling, and multimodal. In the next section, we are going to focus on the assessment of value of the management decisions. And also we have a session on workshop, more discussion and interaction on trial climate services. So this will start in about an hour, which is 12 UTC or 13 British Summer Time or 14 Central European Standard Time, and I'll stop there. There's many other time zones, but this should suffice just to confuse people. And before we wrap up, I should have mentioned at the beginning also the partners, but of course these have been you know, contributing to the presentation, and I thank the contributions for that. And also you've seen many partners also presenting, so you'll see. But at the bottom of the slide, you can see all the partners with UEA. UEA is the University of East Anglia leading the project. We have ENEA, Meteor France, Met Office, UL, KNMI, WMC, URAC, Alperia, and we also have several other, as you mentioned, several other partners, not partners, but industry stakeholders who are contributing very closely to the project with TenneT, Shell, Thames Water, National Grid, and also Celsia in South America. So I think I mentioned everybody, and thank you for the presentations today, the discussion.